And we should be live. I think I am here. Looks like it. Yep, okay. Okay, so we're live then. Let me turn on some... This is where we can add on. If I go turn on some... Yeah, sorry, give me just a second because I'm setting up the stream to be nice. But I am doing this later than I meant to, so it might be... That might be a little bit annoying. Give me just a second here. Let me search or filter. We're looking for... Here we go. Okay, that was probably really loud. Although I did learn that I think that this was less loud for you guys, if I'm not mistaken. I went and looked back at the previous stream, and I think it was less loud for you than it is for me. So let's go ahead and get that out of the way. Okay, we can go ahead and show my face here. Hello. So yeah, I'm going to start off by working on my flashcards for my math exam because that is on Monday at 8 a.m. So I only have a few days left to even use flashcards if I make them. So I'm going to, yeah, that's going to be my primary focus. I'm about, I'd say, between a third and a half of the way through. 2/5 maybe. Wait, is 2/5 greater than a third? I actually don't know that. I feel like it is, right? Because third is 33%, 2/5 is 40%. Yeah, never mind. I was about to look that up. I can't believe I was about to look that one up. Yeah, so, yeah, that's probably more accurate. I'm about 2/5 of the way through these flashcards. I've been working on them for maybe 20-something minutes, so it shouldn't take me too long to do that. And I think after that I want to work on going through some of the homework problems that I missed on the last homework. The subject material is advanced calculus, and I'm doing this. And advanced calculus is basically the course. When I was looking it up, it seemed kind of weird, but it's basically just real analysis, except for only the topics that are sort of related to calculus are covered. So there's a lot about sequences and series, derivatives, integrals, but it covers enough real analysis to sort of robustly build up to that, rather than, you know, your basic calculus, which you know, it doesn't get too caught up in like what defines a limit and what defines all that kind of stuff. So that's the subject material, and I'm right near the end of the course. And so the area that I was working on was sequences of functions. So now let me go ahead and pull up this. Oh, shoot. Do I not have a... Wait, why is this one not showing up? So I have this, right? Oh, that's weird. Why is this one not showing up on my, That's not good. Yeah, it's not... For some reason, the add card thing on Anki is not showing up on my window capture list here. So give me just a second while I figure that out. Maybe I could just do a display capture instead. and then crop it. I think I might do that. So I might do display capture, and then filter, create, we'll say crop. You'll just have to bear with me for a second because I was not expecting this to happen. You also have to bear with me if you see something popping up sort of at the bottom right corner or whatever. It shouldn't happen too much because I should be on streamer mode, but if it does, bear with me. Okay. Close. Okay. That looks pretty good to me. Wait, is it stretching it though? I can't tell if it's stretching it or if the top and bottom windows are set up so that way the resolution would be the same. No, that's not possible, is it? Yeah, because you'd get vertical black bars, not horizontal ones. So if it's still stretching at the end of the screen, if you cut off anything off the bottom without off the top and bottom without cutting anything off the sides, then you're going to end up with an image that's more widescreen, more stretched. So I think it might be slightly stretched, but it's only by like less than 100 pixels. So I don't think it should be enough for it to be extremely weird or noticeable. So you guys can let me know if you feel otherwise, and I'll try to get that changed if so. Now the other thing you guys cannot see is the source material that I'm using. Oh, well actually you can, because oops. Give me just a second. Let me switch to my camera. Alright, I just wanted to make sure I didn't have anything personal there. I had my, it doesn't look like there's anything personally visible there, but that's why I don't like using, I cannot speak. That's usually why I don't like using display capture, because it's way more risky in terms of accidentally showing personal information, which I am not trying to accidentally show any more than I mean to. Okay. So I'm just gonna have like, I'm just moving everything over to my left screen. Okay. So everything is over on my second monitor, so I should not get any more things like that happening unless I'm opening new windows, which I'm not at the moment. So hopefully that should be good. Hope so. Anyways, so what I'm working on now is wait, uniform convergence and continuity. Wait, what am I missing here? How is it? It's weird because this is not the same. This is not the same notation that he was using on the board. So does that mean uniformly continuous instead of just continuous? I might ask that in an email. So I think I might send out an email about that. Send email asking about uniform convergence or sorry, not, sorry, continuity, is what I meant to say. Continuity notation. Because I don't want to get that wrong on the test. Okay. Oh, this is what uniform continuity is. It's saying that this whole thing is uniform continuity. So we'd say, I think that's what we're saying here, is that we're saying that if the function from our domain, like in our sequence, our f sub n being continuous, and we know that f sub n converges uniformly to f, then I know that f is continuous. So it's basically saying, can you take the fact that each of the functions in your sequence of functions is convergent to say that the limit of that sequence of functions is continuous, and that is the case if that convergence is uniform. So we'll say, yeah, uniform continuity. That's basically what that says. So let's add that. Okay, our next one is about uniform boundedness. Oh no, this is a little bit different. So what this one says is that take, so we're going to say that f sub n is bounded on E, and so it's the same logic here, and that f sub n, well, I say logic like this is a logic, this is a theorem which is backed up by like a proof or whatever. This isn't, but it's the same, it's of the same form as uniform continuity. So we can say that f sub n is bound, so if f sub n is bounded on E, and f sub n converges uniformly to f on E, then we can say that f is bounded on E. That's what this is saying. So we basically just do the same thing here as with the other one. So we do this. We do that. Dang it. It always does it with one of these where it just decides. Actually, I'm just going to randomly not include the thing. I know that's because I'm not supposed to. It's basically not how you're supposed to do the Anki with these. But whatever. So I have to rewrite this part. But that won't take too long. This one is just saying f sub n right arrows to f. So, and then this is just E, not f, E. Then we just make sure the spacing is right. Okay, that should be good, I think. So if we know that f sub n is bounded on E and f sub n converges uniformly to f on E, then we know that f is bounded on E. That's our... Okay, and then there was a second part of the theorem which says that Right, so this is a different thing. Then we can say that it's uniformly bounded, but it doesn't actually say what that means. Okay. Let f be bounded on... What just happened? On E, and... Yeah, let f be bounded on E, and let f sub n right arrows to f on E. So we're saying let f be bounded on E and let f then converge uniformly to f on E. Then, oh, I don't know why there's a Z there. Then, I don't know what happened. The sequence of functions the sequence of functions where n is greater than capital N is uniformly bounded. What the hell? What is n then? It just says greater than or equal to n, and then it just doesn't tell me what n is, capital N is at all. Is that the same capital N that we're using? Okay, whatever. So I guess we'll just put this. Whatever. I don't even know what that means, but I'll memorize it anyways. Okay, then we have the uniform convergence theorems for integrals, which states that, so we're going to say we let f sub n be Riemann integrable on the closed interval from a to b, and f sub n converges uniformly to f on the closed interval from a to b. Then let's put this as here. Then we can say that f is Riemann integrable on the same on that same interval, on that same closed interval from a to b. And we can say that the limit as n goes to as n goes to infinity of the integral from a to b of f sub n of x dx is equal to the limit at, or sorry, no limit, is just equal to the integral from a to b of f of x dx. Okay. So let's split this part up. So we'll just say this and that. Boom. As two separate things. Let this and that. And let's add these as separate things. Oh, I didn't mean to do that. I'm just going to do this, and then it's not going to work. Watch this. It worked, actually. Okay, I'll shut up then. Beautiful. Add. Okay, so that's the uniform convergence theorem for integrals. Then we have the bounded convergence theorem for integrals, which states that yeah, I don't like writing theorems as like implications. I like writing it as like I don't like it as saying A, comma, B, comma, C implies whatever. Like I don't like writing it as an if-then sort of implication statement. I like saying let this and this and this and this, therefore whatever. Like a premise, you know, premises, and then conclusion type of like layout, whatever you called that. I want to be careful when I'm saying that, not to phrase that wrong, because I want to be, yeah, I gotta be careful. So we'll say let f sub n and f be Riemann integrable on that same closed interval from a to b, and f sub n converges pointwise to f on that same closed interval AB with f sub n n greater than or equal to capital N being uniformly bounded. Then, sorry. Okay, and then now we can do the block here, and then we can say that the limit as n goes to then we can say that the limit as n goes to infinity of f sub n of x dx is equal to the, or sorry, I forgot the integral part, of f sub n of x dx is equal to the integral from a to b of f of x dx. No, not just, yeah, there you go. So we can just put this one as its own thing, boom, and then we just say put these, boom. We do this. And let's put this one in. Boom. Perfect. Let's add that. Okay, that's the bounded convergence theorem for integrals. And then we need to do the uniform convergence theorem for derivatives. Oh man. Okay, we're almost halfway. Oh, well actually we're more than halfway because it's only half the page for the second part. Okay. Here we go. So the uniform convergence theorem for derivatives is, we're going to say let capital F sub n be differentiable on the closed interval from a to b, and let x null be a point of AB. Then we're about to get, this one's about to be giant. Then we can say that our capital F sub n prime converges uniformly to lowercase f on the closed interval from a to b, and capital F sub n of lowercase x sub 0, or sorry, of x null is how I should phrase that, converging pointwise to a point A, implies okay, I don't understand why it says exists exclamation point F. Is that supposed to say like does not exist? Is that a typo? Or is that just to... I think that might just be making it more explicit. There exists some capital F... Oh, I messed up. In the differentiable AB such that capital F prime is equal to lowercase f, capital F of x null equals A, and nope, I messed up there. And capital F sub n, or sorry, capital F, period. Jeez. All right, so we're saying I have walk like an Egyptian stuck in my head for some reason. Probably because I was listening to it yesterday. It popped up on my on my my YouTube music, and then it was actually kind of catchy. I mean, I'd heard of it before, but I don't know, I wasn't expecting it to be that groovy. It was really good. Okay, so let's just go with that. Let's add that. And then we have here term-by-term derivative for series. Okay, we're so close to the end here. I really don't want to do any more of this. Okay, let's do it. Okay, we're going to start with let lowercase g sub n be differentiable on the closed interval from a to b, and we have x null again, and have x null be in a comma b somewhere. Oh god, this is okay. This is going to be actually kind of weird. Okay, the sum from n equals 1 to, sorry, to infinity of g prime of n or sorry, converges uniformly on a b of g sub n of x null being, when it says less than infinity, that's just like a teacher's notation thing. That's not technically correct. So do not take that as the correct way to write that, because that is a shorthand used by the teacher, but you're not supposed to do that because, well, the notation can be unclear if you don't know what it is, because if it basically it's saying that it converges to a finite value is what the less than infinity means, according to this notation. But that's not at all clear, right? Like if you had it that it diverged to negative infinity, then could you just say that it would be less than infinity, right? Negative infinity is less than infinity. Yeah, it opens up a bunch of things if you tried to take that literally. But it's just sort of a more figurative way of taking the less than and infinity symbol. That I personally wouldn't use, but the professor did, and well, he's in charge of the course, not me, so I'm gonna memorize how to do it his way, because I'm doing a memorization, because this memorization thing is part of my test, and I don't want to memorize it my way. I should be memorizing it his way, because it's his test, you know? Okay. Here we are. It's weird to me that this is phrased as and over here, but over there we put a comma between the ands. Why is it that for the... whatever. Who cares? Oh, I can't even type right now. Jeez. It's not even that complicated, but it's just more, just the notation is so clunky that it feels like I'm like typing out some kind of crazy stuff. But like really all I'm saying here is that if then that would imply that this is differentiable and that the derivative of this is equal to the derivative of the, oh, that's not supposed to be sub n. That's just supposed to be g, wait, no, that is supposed to be sub. This is saying that the derivative of the sum is the same as the sum of the derivative, basically. Okay. Okay, here we go. And then let's do this part. Okay. And then let's just try to, I want to write something before this. let that be the case, then this. Okay. Done. Okay, that should work. Alright, now I'm on the final page, and it's only half a page, so I just have to go through power series, radius of convergence, convergence and divergence of power series, Abel theorem, term-by-term integration and differentiation, and then... wait, it shouldn't be differentiated, that should be... oh, no, it is, okay. And then Taylor's series. Alright, now we go through power series. Man, this is kind of annoying. Alright. Let x null be in the real numbers. Okay, this one I am going to do this in different notation because it's shorter. And the sequence, and let a sub n be a sequence for n in the natural numbers. Which is a subset I thought it was sub EQ, not subset EQ. Okay. Which is a subset of the real numbers. Then so this would be, we'd say, power series, and then let's make this bold, in x minus x null. Hello, Mr. Joker comedians. Hope you're well. Thanks for stopping by. Coefficients. Oh, messed that up. Oh, it looks like that person might be gone. Sorry to hear that. Hope they enjoyed their stay. Dang, sorry, I was tabbed out, so I missed the live chat there. But yeah. Then a power series with coefficients a sub n is and then let's do this. We do a block sum from n equals 0. And that's worth noting that it's from n equals 0 to infinity instead of 1 of a sub n x minus x null to the nth power, which is equal to a null, or I should just say a naught, whatever, a naught plus a1 x minus x null plus a2 x minus x null squared plus dots. Okay. Just go ahead and add that in. Alright, let's just add these. Oh, I misspelled coefficients. Coefficients. Okay, and let us add. Okay, so we've finished the power series definition. Now we're on to radius of convergence. Okay. For a given power series slash sum from n equals 0 to infinity of a sub n x minus x null to the nth for a given power series, its radius of convergence is defined as follows. Sorry about the thing. There was a little issue there with my a couple of these. Okay, hold on. Let me close out of some other tabs on my other stuff, because now that I'm running into this little issue, I think that might help. Okay. Here we go. So for a given power series, its radius of convergence is defined as follows. R equals how do we say this? The okay, is equal to, okay, we're gonna have to do slash left and slash right to make sure that works right. So we'll start with, it is the suplim, or sorry, lim sup, the limit supreme as for n to infinity, the limit supreme of the limit supreme as n approaches infinity of the absolute value, sorry, something like this, the absolute value of a sub n, or sorry, we should say the nth root of a sub n there. I don't know why it's the way that all of that is phrased is weird to me. So it'd be square root, and then we do n of, because we're saying the nth root of a sub n, or sorry, of the absolute value of a sub n. Yes. The limit supreme of that, and then we want to take the, or we're going to take the inverse, or not, sorry. It's 1 over that. The, what is that called? Multiplicative inverse? I think is what that's called. Yeah. Okay. So we have... Yes, I think that's the end of that definition. So let's go ahead and add that. Add that. Oh, there's a problem here. You're not supposed to have 3 in a row here, else it'll mess that up. Okay. Alright, we should be good with that one. Alright, radius of convergence is defined, and now we're looking at the convergence and divergence of a power series. Okay, for a power series, and then we just put in our generic power series, such sum from n equals 0 to infinity of a sub n, it's lowercase n, sorry, of x minus x naught to the nth with radius of convergence r greater than 0. What does that even mean? It diverges, converges absolutely, converges absolute uniformly. Okay, I don't even understand what that means. Alright, I'm lost. Is that saying that each one goes with each thing? Or is it saying that... Okay, because it's... I'll show you the definition here. Because we're looking at this, right? I don't know what the heck the vertical line would even mean here. I don't know if that's supposed to mean that this would apply to all 3 of these, or that this would only apply to this would only apply to this, and that this would only apply to this. Or that all 3 of these would apply to all 3 of these, or all 3 of these would apply to this one. Well, I guess, yeah, all 3 of these. Yeah, so I'm not actually sure what's being asked here, which is kind of frustrating a little bit. Okay, so for this, with the radius of convergence of that, I'm going to take this as it's supposed to be a thing, that we're saying it diverges in this, it converges absolutely in this, and then it converges I don't know what absolute uniformly means. I think maybe that's supposed to say converges absolutely uniformly, but I'm not 100% sure. See, because I don't know what the heck this is. I don't know what any of these are. Is that supposed to say a function that's bounded above by int r? What am I missing here? Because I have no idea what any of this is. Maybe I'm missing something from the lecture notes here. Because if I go back, but I'm kind of worried about that I might be missing something from the lecture notes. Let me go ahead and pull that up. Let me pull up the lecture notes here on my second monitor. Make sure I understand what that says, or what that means. So if I go... Oh, I had to do that. Alright, I'll take care of that today. Wait, what time is it? Okay, so maybe in about an hour I'll move on from this and then work on other stuff, possibly. But I think it's very important that I do well on this. So we have exams, homework, lecture notes. Yeah, lecture notes. So this would be in either lecture 14 or 15. Let me see. This would be lecture 15. That's what that says. Okay. Because I just want to make sure I understand what this says. Aha. So I think it does. It was the interpretation where it's each individually. Left to left, middle to middle. So like, it diverges in this, it converges absolutely in this, it converges absolute, but I don't know what absolute uniformly means. So maybe I should search absolute uniform convergence on Google. Uniform absolute convergence. Maybe that's what we're talking about. In mathematics, uniform absolute convergence, I'm reading Wikipedia here, is a type of convergence for a series of functions. Like absolute convergence, it has a useful property that is preserved when the order of summation is changed. Motivation. Okay, this looks like a... There are like no inline citations at all, which is a little bit wacky, but okay. A convergent series of numbers can often be reordered in a way that the new series diverges. This is not possible for series of non-negative numbers, right? Yeah. Absolute convergence precludes this phenomenon. But when you're dealing with uniformly convergent series of functions, the same phenomenon occurs. The series can potentially be reordered into a non-uniformly convergent series, or a series which is not even converge pointwise. This is impossible for series of non-negative functions, so the notion of uniform absolute convergence can be used to rule out these possibilities. So that would be to say, I think that's the Weierstrass M-test. That's what the, right, I think that's what the, right, because it says this, I think, which is what, this is the thing we're talking about right here. This one, that the so the absolute value of these functions is uniformly convergent. Yes. Oh, here we go. We can see that the absolute value converges uniformly. So uniform absolute, so it's actually uniform absolute convergence is the correct way to say that, instead of converges absolute uniformly. We would say is uniformly absolutely convergent. Uniformly absolutely convergent. Jeez, it's kind of a weird way of phrasing that. Okay, but I'm going to go ahead and move this back over here so we can work on writing this. And now that we know what this is saying, because we need to put these in three different things, because they're three different statements. I don't know why it's stated as if they're the same one. For a power series with a radius of convergence that is greater than 0, it diverges in the real numbers. Oh, not lowercase r, capital R. In R set minus see, I just don't know what the B Is that saying bounded B sub R? Yeah, I don't know what that notation is trying to say. I guess I could look at the textbook. That's also a possibility. I could be looking at the textbook here for this. But I don't want to get too caught up in trying to figure this out. But I just need to know what that means. I think that means bounded above. B sub R of x0 with a overline. It is kind of confusing what that means. Okay, let me see if that's explained in the lecture notes. Maybe not. So yeah, I'm not seeing anything about that here. Okay, maybe that's back here. Looking in the previous slide, or in the previous lecture notes to see if there's anything about this. Yeah, I'm not seeing anything about that. See, I think that this is a notation that that the professor used in the first set of courses. My guess is that he's saying that it is bounded above. But I don't know what the sub R would mean. Is it saying that it's bounded, that x0 is bound, or sorry, x null is bounded above by R, but then, yeah, no, I'm not sure what that means. For a power series, the radius of convergence, it diverges in, huh? Okay, I think there's a video by the Bright Side of Mathematics that I could watch, so let me see on this subject. So I might do that. Might do. Bright Side of Mathematics Real Analysis. Sorry, I don't want to steal his stuff, so I'll... See, I'm not sure whether I'm allowed to show these on stream. I think I don't think I get DMCA'd for it, or if I would, then I'll take the stream down. But reordering, sequence of functions, pointwise convergence, uniform convergence, limit of functions, continuity in examples epsilon delta, combination of continuous functions. I'm looking for power series. Taylor's theorem. The Weierstrass M-test. Wait, hold on. Actually, what am I talking about? I'm talking about the convergence of power series. Let me just search this up. Or actually, no, I'm gonna look this up in the textbook. Give me just a second for me to pull up the textbook to see what it says. Sorry you guys aren't getting to see very much here. I guess I can switch it to a camera like that. Because you guys aren't really getting to see anything because I'm just like searching stuff up here. Images. Excuse me. Here we go. This is the book I'm looking for. Alright, and in the lecture notes, it's on 8.7.3 is the theorem. Diverges. Okay. What a... Okay, yeah, okay, it makes so much more sense in the way that it's formulated in the textbook. I don't know why that would get updated to what they changed it to here. It just makes no sense. Okay. Alright, we'll switch back. Okay, so what they're saying is that it... For... What the heck just happened? Sorry. It diverges... Oh, can't type. Diverges for all x where... and then all... where the absolute value of x minus x naught is... What is this? Greater than r? Is that what I'm... I think that's what it says. Radius of convergence R, we're saying... Yes, that's true. Diverges for all x with that. Yeah. Okay. Yeah, why don't we just... Okay. Whatever. That's not really even my thing to judge on why it's written that way. So let's go ahead and add one here. We'll just put this. There we go. That's what we'll put for that one. Nice. Okay, we'll take that. We got our next one. Okay, what's our next? Ooh, that could be fun. I might do that at some point. Yeah, that's not, yes, I do want to do that at some point, but that's after I finish this. I just want to finish this dang thing. Okay, now what I want to do is, let me grab the previous one, and I'm just going to, like, straight up copy this. Let me just copy this straight up. Copy. Like this. Okay. Alright. For a given power series, this one, it's... Wait, no, that's the wrong... Sorry, that's the wrong thing. I don't know why it's... What? I don't understand. Why is this looking at the wrong one? This is not what I was looking at. I'm saying what was my previous thing. Oh, did I click... Oh, I clicked to previous. Okay. Okay, yeah, that's what I did. I just realized. This was my mistake. Okay, there we go. I was just trying to copy paste that fast. So we had that it diverges for this, and we'll have... Ooh, okay, hold on. Let me look at the previous one. Give me just a second. I want to look at the previous one. I'm going to change it, so that way this, let me add in this one. That is a different thing, like that. Okay, so then now we got this one. And then we're looking at it converges, absolutely. And then let's add that as a separate thing. And then we're saying for all x with, instead of greater than, this should be less than. Yes. Yep. Okay. Yep. Okay, that should be correct. Okay, and then now we are on to the last one. So this last part says, it absolutely uniformly converges. Okay, so we could say, another way of saying this is, we just paste this in here again. Greater than, or sorry, is less than or equal to row. So we change this, needs to be less than or equal to. Where, hello, sorry. And then we'll just say for all row less than R. There we go. And then instead of converges, we'll say it is absolute. Wait, is it uniformly absolutely convergent or convert? I've already forgotten what it was. Give me just a second. I gotta Google that again. I had it on here. It's uniform. It is uniform. What would we say? It absolute is uniformly absolutely convergent. Is uniformly absolutely convergent. Oh, get rid of that. Let me add that. There we go. There we go. That should be good. Yes. Add. Okay, that should be done. Okay, so we're on to the next one. Okay, Abel's theorem. We're down to the last three. We just have Abel's theorem, term-by-term integration, differentiation, and then Taylor series. And then we should be done with these note cards. And then after that, I want to start practicing the note cards. Okay. Get rid of that. We don't need that anymore. Okay. So Abel's theorem states that if we let f of x be a sum from n equals 0. Sorry, this is just basically we're saying it's a power series. Oh, sorry, I forgot to actually include this part. A sub n times x minus x naught to the nth with a radius of convergence r greater than 0. Then okay, then there's three different things which are all true. So the first one, so we'll say A, B, and C. And then we'll just stick it. And it needs to be inline instead of how I'd want it to be, which would be block form, but when you have it wrapped in a list, you actually can't do that. It doesn't work properly, unfortunately. It'll look right in the preview, but it won't actually work on the thing, like on the actual presentation. Okay, so these were basically then the following are true. Hello? Why are there 3 L's? Are true. I don't know why sometimes it's getting so laggy here. Then we can say that F is... Sorry. F is continuous. Oh, hello. Continuous on the closed interval. Sorry. Gosh, I don't know why it's math cal on the open interval x naught minus r to x naught plus r. Hold on, give me 1 second. Why is I have to keep tapping back into this for this to start playing. There we go. Yeah, I'm starting to get a little bit hungry here, so I mean, I'm definitely gonna finish, or I'm gonna stay on until probably 7, but then after, or well, 7 Eastern, so 1900 Eastern, whatever. So just a few more minutes here. So we have that F is continuous on this. We have... Okay, the second one is this one. First of all, we have to... Wait, no, we don't even need to do display style. I think by default it puts it in display style. Like if I do /sum n equals 0. Yeah, it does it display style by default. Which is nice. I appreciate that. Sometimes with the inline thing, what it'll do is it'll put the n equals 0 and the infinity, it'll put it like along the bottom and top, which is annoying and not what I would want. So I'm glad to hear that that is not the case here. Once again, to be clear, the less than infinity does not actually mean less than infinity. It means that it converges to a finite value, which is less than it. Yeah, that it converges to a finite value. Say implies... Oh, I see. Implies F is continuous Okay, yeah, this is basically saying that you can, is that you know for a fact that it's continuous on this open interval, and then if you have to manually check the endpoints, basically, is what that's saying. On x naught minus r to x naught plus r, but then this one is closed. And then let's and then for our last one, we basically, it's the same thing as this part, although that's not the way we copy it. Break. Okay, whatever. Yeah, I'm not really sure what's going on there. Okay, well, slash sum from n equals, oh, sorry, n equals 0 to infinity of a sub n of negative r to the n being or converging to a finite value implies that f is continuous on x naught minus r to x naught plus r. Like that. Oh. There we go. Alright, so those are our three things that are implied here. So let's take each of these and we'll add in a thing here. And I want to be very careful because I do not want this to get deleted, because if it does, I'm going to be very upset. Oh, none of it did. Thank gosh. Thank gosh. I think I know what causes it. So, I appreciate. So, I think I should do better on that from now on. But anyways. I think that's everything here. Oh wait, no, hold on. I gotta turn that into that. Okay, so we got this. We're gonna add that. So that one is Abel's theorem. Okay, then next we have term-by-term integration and differentiation. Wait, didn't we already do term-by-term term-by-term derivative for series? Oh, this is... Huh? Okay. I think that's a different thing. Okay. Oh, these are two things wrapped into one. All these last ones, they're like two different theorems, but then they're phrased as if they're one theorem. So I'm going to have to split them up. So we're saying let f of x be... Oop, not x naught. F of x be the sum from n equals 0 to infinity. Oh my gosh, how many times am I going to have to write out this stupid power series formula? I'm getting so tired of it. I could like set up like a macro or something for it, but at this point I'm so close to the end that it's just not even worth it. But if I had realized how many times I'd be rewriting that over and over again, I think I would have written a macro to just type the same thing out over and over again, because I'm so tired of typing that out. With a radius of convergence r greater than 0. Then I mean, I guess what I can do is I could do basically the same thing I did with the previous and instead turn it into a list like this. We'll say that the integral from x naught to x of f of s ds, which I'm pretty sure the reason why... So I think s is only used technically as a change of variable, but I think the reason why s is the variable used instead of t, which is traditionally what you'd do, is because I think s means it could be complex, whereas t does not. But I don't know if that's necessarily implied. But I might also be misremembering that, because now I'm thinking that it has to do with something completely different. I don't know. If anybody knows, they can leave a comment or chat. So, doesn't look like anyone's watching at the moment, but yeah, if you're watching this VOD and you know a bit more about this stuff than I do, so then go ahead, drop a comment. I'd love to learn a little bit more about this kind of stuff. because admittedly it does confuse me a bit. Then we're saying that this is equal to the sum from n equals 0 to... Although part of that is my fault for... sorry, wait, hold on. I already did this sum. I just typed that in twice. Of the following fraction. A sub n over n plus 1 times... Oh, we're going to do another x minus x naught to the n. Oh, this time... Oh, actually, no. This time it's to the n plus 1. Look at that. Okay, I guess we could phrase it this way, but can't you just say it's the same thing except for... Wait, no you can't, because the a sub n would not be moved. I was going to say, couldn't you just change n to be equal to 1 instead, but then you would be off by 1. That makes sense, actually, because if you're dealing with a power series, then it's basically... It's like a, what do you call that? Polynomial. Or whatever, so you're just going to end up with the integral term. Oh, that's why it's called term-by-term integration. That makes sense. So we'll say with the same radius of converge, and I've lost it because it's taking so long for that to load for some reason. With the same radius of convergence, and then we'll do basically the same thing, but this time we're looking at, instead of the integral, we're looking at the derivative, but it's the same idea, is that f prime of x is equal to the sum from n equals 1 to... Oh, that's worth pointing out that that's from 1 to infinity instead of 0. Wait, but that actually... No, that does make sense. Because you're going to end up with one less term if you're... or your term's going to start... Because you get rid of the constant, right? You're getting rid of your a naught from your power series if you're taking the derivative. That makes sense. Is equal to n a sub n of x minus x naught to the n minus 1 with the same radius of convergence. Okay, so then now we just need to boop, boom. Then let's do this. Boop. Boom. Boop. There we go. Okay. That should be good. Exam 3, add. Okay, and then now we're down to the last one, which is the definition of a Taylor series. Although I don't know how much that's going to play in. Here we go. Let f of x be defined as that power series we were just working with. Be defined as the sum from n equals 0 to infinity of a sub n times x minus x naught to the nth power with a, or sorry, it shouldn't say a radius of convergence, it should say the radius. Or sorry. Well, the problem is a radius makes it sound like there's multiple radiuses, but I don't think that's actually what I'm looking for here. Oh, thank you, Vatsan Arunan. Vatsan? I'm sorry if I've butchered your name there. But I appreciate you. Yeah, I appreciate you, man. That's really nice of you. Thank you. Okay. Taylor series with a radius, with a radius of convergence, non-zero radius of convergence, basically. R greater than 0. Boom. Then we can say these two things. I don't know if we should put this like that. Let's put this as this. Actually, no, this is probably notation is probably the best way to do it. We're saying that it is continuous. It's infinitely continuous, meaning that if you differentiate it, no matter how many times you take the derivative of it, it stays continuous. Like that. On the open interval x naught minus r to x naught plus r. And then here's the second one. We get that a sub n is equal to the following fraction. This would be a derivative here. The nth derivative of f at the point x naught over n factorial. Okay. And then put a period here. And then we get this. We got boom. And we get boom. Here we go. Oh, there we go. All right. I think that is everything. So we add, and then I think I should be done. So yes, okay, I finished with those note cards. That took me way too long. I have about 30 minutes to practice them, because I want to hop off and move away from this, because I gotta go get dinner for myself and stuff after this. So I think the stream should be around until then. But in the meantime, let me go ahead and close out of that, and let me pull up the thing so you guys can do that with me here. Give me just a second so I can close out of all these tabs that I have open for this. That got open. Close out of that, and that, and that, and that. And then I can give me just a second here while I pull this up. Window capture. And let's have this open on this over here. Uh-oh. So if I have it set to this, I would need to do I'm not sure why the window capture seems to be so butchered by the, yeah, for some reason it seems to be completely Hold on. Give me just a second so I can put this one out here. I want exam 3. Yeah, I only want the exam 3 ones. Yep. Okay, here we go. So there's 63 cards here. So I think I gotta turn... I think I want to have this back up here again. Alright. Here we go. So we're gonna go ahead and do this. We got 63 to revise on here. So we're gonna say let f of f sub n be a series of functions. Let there be a series of functions, and let f be let f be a function that maps values of e to the real numbers, then we say that f sub n converges uniformly to f on e if for all, what is it? It's for all, shoot, I think it's for all n greater than 0. Or no. Does it start with epsilon or n? I think it's for all n greater than, or so for all natural numbers n, and for all, or not and, we'd say for all natural numbers n, for all epsilon greater than 0, the absolute value of f sub n minus f is less than epsilon for all n greater than capital N and... Oh man. Okay, this is rough. I don't think I'm going to get this first try. No. Okay, let me see if I can look back at this while I hold on, let me change something. There we go. Change the title. And let me add in a little stream marker there to make that clear. Okay, so I got that one wrong. So the correct answer is for every epsilon, so I should start with epsilon. For every epsilon, there is a natural number, capital N, such that for all n greater than capital N, greater than or equal to capital N, and for all x in E, the absolute value of f sub n of x minus f of x is less than epsilon. Okay, so let's go ahead and do that one again. So I'm saying let... Wait, is this done in... Hold on, what order is this done in? Sorry, give me just a second. Give me just a second here. What's going on? I just want to make sure that this is not doing it in... limit... Yeah, I don't see a way to do that. I don't think that there's any options. Yeah, no, it is random. Okay, never mind. Just wanted to make sure that was random. I didn't want to accidentally be doing the wrong thing there. Okay. Alright, we're chill. Let's go back here. Okay, here we go. So I'm saying let f... Sorry. This is uniform continuity. So I'm saying let f be continuous, I think. Please be right. F be continuous? Oh, I accidentally added a second marker there. Nope, just needs to be integrable. Dang it. I don't even know what this is called. Whatever. So I'm saying let f sub n be integrable on the closed interval from a to b. That, and that. Okay. Let's try. Okay, here we go. Let the... Alright, we have a series of functions, f sub n, and we have f, our function f, a real function f. Then we say that f sub n converges uniformly to f on e if, for all epsilon greater than 0, there exists a capital N in the natural numbers such that for every lowercase n which is greater than or equal to capital N, for all x in E, the absolute value of f sub n of x minus f of x is less than epsilon. For all epsilon greater than 0 exists a capital N in the natural number such that for all lowercase n which are greater than or equal to capital N, for all x in E, the absolute value of f sub n of x minus f of x is less than epsilon. Yes, I got that one right. Nice. Okay. So I'm saying let f be Riemann integrable on the closed interval from a to b, and f sub n converge uniformly to f on ab. Then f is Riemann integrable on ab, and the limit of the integral of f sub n is equal to the integral of the limit. That's what that says. So that is correct. All right. Okay, I assume capital F needs to be differentiable on the closed interval from a to b here for this. What's going on? Why is this bugging out here? Yep, there we go. Then yes, so that's correct. Okay, let x naught be Riemann integrable, and what does that mean? X naught being a Riemann integrable? I think that should be real numbers. I think I messed that one up. Let x naught be a real number, and we have something else here. What else do we need for it to be a power series? Oh, that we need the sequence a sub n, and the sequence a sub n I don't remember what the deal was. It needs to be a real subset of the real numbers. Damn it. Okay. Let's try that one again. All right. Let there be a series of functions f sub n, and f be a real function. Then we say, or series of real, sorry, f sub n is a series of real functions, and f be a function. Then we say that the sequence of functions f sub n is uniformly Cauchy if okay, so I think it's shoot. I think it has to do with the sup norm. So I think the sup norm of f sub n minus f sub m is less than, oh sorry, I forgot this. For all epsilon greater than 0, f sub n minus f sub m, or sorry, the sup norm of f sub n minus f sub m is less than epsilon for all x in E. Right? Oh, okay. The sup norm goes to 0 as n and m go to infinity. Okay. Dang it. Try that one again. Alright, let x not be, I'm just going to assume that's supposed to be a real number. Let x naught be a real number, and the sequence a sub n needs to be a subset of the real numbers. Yes. Alright. F sub n is bounded on E, and I think we need that F sub n converges uniformly to F on E. There we go. That's correct. So let G be a function from... Uh-oh, yeah, this one is poorly written. I think this one was supposed to be the definition of soup norm, and I do know what that is, but I just need to... move that like that. Boom. There we go. Okay, then the, let G be a function from E to R, E to the real number. So let G be a real function. Then, G, then the soup norm of, G is defined as the supremum, the supremum for x and E of G, or of the absolute value of G of x, I think. Yes, correct. We'll put that as difficult there. Okay, so let F... Alright, be a series of... let there be a sequence of functions Fn and Fb... a series of... not a series. Let there be a sequence of real functions Fn and F be a real function. Then we say that the sequence of functions Fn is uniformly Cauchy if wait, when do I say that? Oh, give me just a second. We're good. We say that it's uniformly Cauchy if f sub n... No. Shoot, I've already forgotten. Dang. Yeah, I've already forgotten. F sub n is uniformly Cauchy if... Oh, sorry. If the soup norm of f sub n minus f sub m is less than epsilon as n and m approach infinity. Sorry, not is less than epsilon, tends to 0. Okay, so let x naught be a real number, and a sub n be a sequence of real numbers, then a power series. Yeah. Okay, that one's easy. Okay, for a power series, that one with a radius of convergence blank. R greater than 0. Okay, so let Fn, sorry, okay, this is, we'd say that f is, or no, f or fn? We say fn is uniformly Cauchy. Oh, I wasn't paying attention. Oh, man. Okay. Got that one wrong. Okay, I definitely need to study this. Okay, so let that, we say that f is uniformly Cauchy if, okay, here we go. The sup norm of fn minus fm tends to 0 as n and m tend to infinity. Yes, let's go. So here we go. Oh, sorry, x naught just has to be a real number. Hold on. Let me just change this so this one's correct. There we go. Okay, correct. Let gn be differentiable on AB, on closed interval AB, and x naught be an AB, then what implies that I think it's that if the sum of g n is converges uniformly on AB. Nope. Okay. Correct answer is if the sum of g prime n converges uniformly on AB, and the series g sub n of x0 converges to a finite number, then you can say that. So, okay. Wait, I got that. I don't know what the deal is with that. All right. We would say that, we'd say that fn converges to f with respect to sup norm. If, yeah. Correct. All right. Are we just saying that fn is a series of functions, or what are we saying? Oh, no, we need to say that fn is bounded, I think, is what we're saying. Yeah. Yeah. Fn is bounded on AB. No. No. We're saying that it's Riemann. Oh, we have that it's uniformly bounded here. No, we need to say that they're both Riemann integrable. Okay. Let Gn be differentiable on AB and x naught be in AB. Then the sum of Gn prime converging absolutely and and the sum of gn gn of x naught converging to a finite value implies all of that stuff. There we go. All right, let f n be a sequence of functions and f be a real function. Then we say that the sequence of functions fn is sup norm convergent. Or sorry, no, sorry. Is uniformly Cauchy. Let me see. I don't know why it keeps doing this. It's uniformly Cauchy. That is correct. Okay. So let fn and f both be, what do you call it? Both be a Riemann integrable on AB. Alright. So let f of x be equal to the sum, or sorry, let f of x be a power series with a radius of with a positive radius of convergence. Then we can say the following. So then we can say that the integral from x naught to x of f of s ds is equal to the sum from n equals 0 to infinity of a sub n over x minus 1 times x minus x naught to the, or sorry, before when I said n minus 1, I should have meant n plus 1. It should be to, yeah. So it should be, sorry, let me restate that. The sum, or the integral from x naught to x of f of s ds is equal to the sum from n equals 0 to infinity of a sub n over n plus 1 times x minus x naught to the n plus 1 with the same radius of convergence. Correct. Nice. So let x naught be real number, and we also need that a sub n is a real sequence. Or is a sequence of real numbers. Okay, that one's easy. Okay, let g be a function, or a real function. Then the sup norm of g is defined as, the sup norm of g is defined as the supremum with x in E of why am I blanking on this? Oh, sorry, of the absolute value of g of x. Correct. Don't know why that took me so long to remember. I think I'm just kind of pooped here. Let f, n, and f both be Riemann integrable, and we have, I think they need to be, okay, if we have them being uniformly bounded, I think we can just say that their fn converges pointwise to f on AP, yeah. So that's correct. Okay. We have gn is differentiable on AB, and that x naught is in AB. Yeah, that one's easy. Our power series with a radius of convergence R, with a positive radius of convergence, it diverges for all x where x minus x naught is greater than R. I forgot to say absolute value, but I would have put absolute value, so. But anyways, looks like right now it's pretty much time to end the stream, so we're right at the end. But I hope you enjoyed. It was a way more single focus stream than my previous ones, so instead of working on a bunch of different things, I've sort of stuck to just the one, which was, in this case, why is this not working? Weird. There we go. Which, yeah, I mean, I think it went pretty successfully overall. I got through all the cards that I wanted to. Now, I didn't expect it to take an hour and a half to do that, especially since I had already spent like a good 20-30 minutes on it. So I mean, that's 2 hours total. It took me to completely finish all the flashcards, which I was not expecting it to take that long. But I mean, it is what it is, and I got it done, and I'm glad that I got it done. So yeah, I mean, I'd say overall pretty good, pretty happy with it. I think these are going to be good things to study. Like, in terms of how well I know this stuff, I feel like I got a slightly better understanding as I was writing out all of them, but not good enough. So I think as I continue, I'm going to probably stream tomorrow, and tomorrow I'm going to go over the flashcards for a bit, and then I'm going to start trying to actually apply them by going over some of my previous homework in that class, like basically do practice problems on it. But then after that, I'm trying to think. Let me see. I have a little list for what I want to get done tomorrow. I think. Oh, there's some other things I need to get done tonight, but those are things I can't do on stream. I need to do some course evaluations, but obviously that'd be kind of weird to stream that, talk about my professors like that. That'd be kind of weird. And there's a couple of other things that were just basically need to get done, but I probably would not feel comfortable sharing it on a live stream. So yeah, I hope you enjoyed. It was an overall pleasant experience, although it did get a little bit frustrating towards the end there. Yeah, so if you're watching this as a VOD, I hope you enjoy it. Be sure to drop a like or a comment. I appreciate feedback if you'd like to give it. If not, that's cool as well. So I hope you have a fantastic rest of your day. But yeah, peace everyone.